Crystallization is the process of formation of solid crystals precipitating from a solution, melt or more rarely deposited directly from a gas. Crystallization is also a chemical solid-liquid separation technique, in which mass transfer of a solute from the liquid solution to a pure solid crystalline phase occurs. In chemical engineering, crystallization occurs in a crystallizer. Crystallization is therefore an aspect of precipitation, obtained through a variation of the solubility conditions of the solute in the solvent, as compared to precipitation due to chemical reaction. Process. See also Crystallization Dynamics section. The crystallization process consists of two major events, nucleation and crystal growth. Nucleation is the step where the solute molecules dispersed in the solvent start to gather into clusters, on the nanometer scale, that become stable under the current operating conditions. These stable clusters constitute the nuclei. However, when the clusters are not stable, they dissolve. Therefore, the clusters need to reach a critical size in order to become stable nuclei. Such critical size is dictated by the operating conditions. It is at the stage of nucleation that the atoms arrange in a defined and periodic manner that defines the crystal structure. Note that crystal structure is a special term that refers to the relative arrangement of the atoms, not the macroscopic properties of the crystal, although those are a result of the internal crystal structure. The crystal growth is the subsequent growth of the nuclei that succeed in achieving the critical cluster size. Nucleation and growth continue to occur simultaneously while the supersaturation exists. Supersaturation is the driving force of the crystallization. Hence the rate of nucleation and growth is driven by the existing supersaturation in the solution. Depending upon the conditions, either nucleation or growth may be predominant over the other, and as a result, crystals with different sizes and shapes are obtained. Once the supersaturation is exhausted, the solid-liquid system reaches equilibrium and the crystallization is complete, unless the operating conditions are modified from equilibrium so as to supersaturate the solution again. Many compounds have the ability to crystallize with different crystal structures, a phenomenon called polymorphism. Each polymorph is in fact of different thermodynamics. Solid-state and crystal polymorphs of the same compound exhibit different physical properties, such as dissolution rate, shape, melting point, etc. For this reason, polymorphism is of major importance in industrial manufacture of crystalline products. Crystallization in nature. There are many examples of natural process that involve crystallization. Geological timescale process examples include natural crystal formation, stalactite, stalagmite, rings formation. Usual timescale process examples include snowflakes formation, honey crystallization. Artificial methods. For crystallization to occur from a solution, it must be supersaturated. This means that the solution has to contain more solute entities dissolved than it would contain under the equilibrium. This can be achieved by various methods, with solution cooling, addition of a second solvent to reduce the solubility of the solute, chemical reaction and change in pH being the most common methods used in industrial practice. Other methods, such as solvent evaporation, can also be used. The spherical crystallization has some advantages for the formulation of pharmaceutical drugs. Crystal production from a material industry perspective. Macroscopic crystal production. For supply the demand of natural light crystals with methods that accelerate timescale for massive production and or perfection. Ionic crystal production, covalent crystal production, tiny size crystals, powder, sand and smaller sizes. Using methods for powder and controlled forms. Mass production. On chemical industry, like salt powder production, sample production, small production of tiny crystals for material characterization. Controlled recrystallization is an important method to supply unusual crystals. that are needed to reveal the molecular structure and nuclear forces inside a typical molecule of a crystal. Many techniques, like X-ray crystallography and NMR spectroscopy, are widely used in chemistry and biochemistry to determine the structures of an immense variety of molecules, including inorganic compounds and biomacromolecules. Thin film production, purification used to improve or verify their purity. Crystallization separates a product from a liquid feed stream, often in extremely pure form, by cooling the feed stream or adding precipitants which lower the solubility of the desired product so that it forms crystals. Well-formed crystals are expected to be pure because each molecule or ion must fit perfectly into the lattice as it leaves the solution. Impurities would normally not fit as well in the lattice, and thus remain in solution preferentially. Hence, molecular recognition is the principle of purification in crystallization. However, there are instances when impurities incorporate into the lattice, hence, decreasing the level of purity of the final crystal product. Also, in some cases, the solvent may incorporate into the lattice forming a solvate. In addition, the solvent may be trapped within the crystal formed, and this phenomenon is known as inclusion. Typical equipment for the main industrial processes for crystallization. Tank crystallizers. Tank crystallization is an old method still used in some specialized cases. Saturated solutions, in tank crystallization, are allowed to cool in open tanks. After a period of time the mother liquor is drained and the crystals removed. Nucleation and size of crystals are difficult to control. Typically, labor costs are very high. Thermodynamic view. The nature of a crystallization process is governed by both thermodynamic and kinetic factors, which can make it highly variable and difficult to control. Factors such as impurity level, mixing regime, vessel design, and cooling profile can have a major impact on the size, number, and shape of crystals produced. Now put yourself in the place of a molecule within a pure and perfect crystal, being heated by an external source. At some sharply defined temperature, the complicated architecture of the crystal collapses to that of the liquid. Textbook thermodynamics says that melting occurs because the entropy gain in your system by spatial randomization of the molecules has overcome the enthalpy loss due to breaking the crystal packing forces. This rule suffers no exceptions when the temperature is rising. By the same token, on cooling the melt, at the very same temperature the bell should ring again, and molecules should click back into the very same crystalline form. The entropy decrease due to the ordering of molecules within the system is overcompensated by the thermal randomization of the surroundings. Due to the release of the heat of fusion, the entropy of the universe increases. But liquids that behave in this way on cooling are the exception rather than the rule, in spite of the second principle of thermodynamics. Crystallization usually occurs at lower temperatures. This can only mean that a crystal is more easily destroyed than it is formed. Similarly, it is usually much easier to dissolve a perfect crystal in a solvent than to grow again a good crystal from the resulting solution. The nucleation and growth of a crystal are under kinetic, rather than thermodynamic, control. Crystallization dynamics. As mentioned above, a crystal is formed following a well-defined pattern, or structure, dictated by forces acting at the molecular level. As a consequence, during its formation process the crystal is in an environment where the solute concentration reaches a certain critical value, before changing status. Solid formation, impossible below the solubility threshold at the given temperature and pressure conditions, may then take place at a concentration higher than the theoretical solubility level. The difference between the actual value of the solute concentration at the crystallization limit and the theoretical solubility threshold is called supersaturation and is a fundamental factor in crystallization dynamics. Supersaturation is the driving force for both the initial nucleation step and the following crystal growth, both of which could not occur in saturated or undersaturated conditions. Nucleation. Nucleation is the initiation of a phase change in a small region, such as the formation of a solid crystal from a liquid solution. It is a consequence of rapid local fluctuations on a molecular scale in a homogeneous phase that is in a state of metastable equilibrium. Total nucleation is the sum effect of two categories of nucleation, primary and secondary. Primary nucleation. Primary nucleation is the initial formation of a crystal where there are no other crystals present, or where, if there are crystals present in the system, they do not have any influence on the process. This can occur in two conditions. The first is homogeneous nucleation, which is nucleation that is not influenced in any way by solids. These solids include the walls of the crystallizer vessel and particles of any foreign substance. The second category, then, is heterogeneous nucleation. This occurs when solid particles of foreign substances cause an increase in the rate of nucleation that would otherwise not be seen without the existence of these foreign particles. Homogeneous nucleation rarely occurs in practice due to the high energy necessary to begin nucleation without a solid surface to catalyze the nucleation. Primary nucleation has been modeled with the following. B is the number of nuclei formed per unit volume per unit time. N is the number of nuclei per unit volume. Naught is a rate constant. C is the instantaneous solute concentration. C** is the solute concentration at saturation, is also known as supersaturation. N is an empirical exponent that can be as large as 10, but generally ranges between 3 and 4. The first type of known secondary crystallization is attributable to fluid shear, the other due to collisions between already existing crystals with either a solid surface of the crystallizer or with other crystals themselves. Fluid shear nucleation occurs when liquid travels across a crystal at a high speed, sweeping away nuclei that would otherwise be incorporated into a crystal, causing the swept-away nuclei to become new crystals. Contact nucleation has been found to be the most effective and common method for nucleation. The benefits include the following: low kinetic order and rate, proportional to supersaturation, allowing easy control without unstable operation. Occurs at low supersaturation, where growth rate is optimum for good quality. Low necessary energy at which crystals strike avoids the breaking of existing crystals into new crystals. The quantitative fundamentals have already been isolated and are being incorporated into practice. The following model, although somewhat simplified, is often used to model secondary nucleation. K1 is a rate constant. Mount is the suspension density. J is an empirical exponent that can range up to 1.5, but is generally 1. B is an empirical exponent that can range up to 5, but is generally 2. Crystal growth. Once the first small crystal, the nucleus, forms, it acts as a convergence point for molecules of solute touching, or adjacent to, the crystal so that it increases its own dimension in successive layers. The pattern of growth resembles the rings of an onion, as shown in the picture, where each color indicates the same mass of solute. This mass creates increasingly thin layers due to the increasing surface area of the growing crystal. The supersaturated solute mass the original nucleus may capture in a time unit is called the growth rate, expressed in kilogram, and is a constant specific to the process. Growth rate is influenced by several physical factors, such as surface tension of solution, pressure, temperature, relative crystal velocity in the solution, Reynolds number, and so forth. The main values to control are therefore supersaturation value, as an index of the quantity of solute available for the growth of the crystal; total crystal surface in unit fluid mass, as an index of the capability of the solute to fix onto the crystal; retention time, as an index of the probability of a molecule of solute to come into contact with an existing crystal; flow pattern, again as an index of the probability of a molecule of solute to come into contact with an existing crystal. The first value is a consequence of the physical characteristics of the solution, while the others define a difference between a well and poorly designed crystallizer. Crystal size distribution. The appearance and size range of a crystalline product is extremely important in crystallization. The importance lies in the fact that large crystals are easier to filter out of a solution than small crystals. Also, larger crystals have a smaller surface area to volume ratio, leading to a higher purity. This higher purity is due to less retention of mother liquor, which contains impurities, and a smaller loss of yield when the crystals are washed to remove the mother liquor. The theoretical crystal size distribution can be estimated as a function of operating conditions with a fairly complicated mathematical process called population balance theory.